Hello everyone. So in my last video, I'll show you how to run a local LLM model on your PC. And if you have actually tried it, you have probably reached one of the two outcomes. First, your model will run perfectly fine on your hardware, giving you decent amount of speed and response from your AI model. Or, you could have faced the same issue as me, only getting 7 tokens per second, which is kind of slow and laggy, and is a bit of unusable in this case. Like we are talking about around 7 tokens per second. That is basically so slow that you have to wait for a simple response. So I did some research over the past week to understand about LLM model and especially the model I'm running. So today I'm going to show you how to make your local LLM way faster without upgrading your hardware. Also because of this, I understand why it was very slow on my system, what was the cause and how do we resolve this issue. So first we need to understand the model we are running and how to split your model correctly between CPU and GPU layers. So if you are using the 35B mixture of expert model like me in this video, we need to know that not all the weights are used at the same time. So instead we put the handling parts on the GPU layer, like Chrono has mentioned, such as attention, gate and context in the comment of my previous video, and put the mixture of expert layers, which is the thinking part, to CPU. Why this will work? Because we need to understand that for mixture of expert model, which is in this case we are using CRAN 3.6 35B A3B model, while this is a 35B model, but at any point in time there will only be 3B active. So the remaining 32B are asleep. In this model, there are 256 experts, and only 8 experts will be activated depending on the task. The gating network, in layman terms a router, will determine which 8 experts to activate for your task. So to summarize, since the expert layer are not always in use, it is better to put them to CPU to free up some space in your GPU, especially if you do not have enough VRAM in your GPU to hold the whole model. This one is very important because we need to understand the model you're running and how many layers are in the model and how much memory available that we have in our CPU and GPU to allocate to the LM model. So next, I will run the model on my local PC and we will see what is the issue that we have faced in our previous video. So this is exactly the same command that I ran in my previous video. Okay, now that the model is running, we can try to talk to the model. And as you can see, it is very slow and it's kind of laggy in a sense, right? I mean, it's kind of getting stuck. This is really not usable in the sense that how long do we have to wait for a simple hello, how are you? So if you are going to use this as your AI assistant, that is not feasible, right? I mean, like, you're not going to wait so long just for one simple response. We will look into why it is so slow, and I previously mentioned. So the main issue here was with these parameters and CPU MOE. So these parameters actually determines how many of your expert layer are pushed to your CPU, which is your RAM in this case. So there are 40 layers of MOE in this model that I'm running, and I'm pushing only 21 layers to the CPU. This means that 19 layers are running in my GPU. And so why did I use these parameters? This number, right? Who determine how many layers of MOE to push to the CPU, correct? So in this case, it was working for me when I'm not recording. And the reason why is, when I'm not recording, I'm not running my virtual avatar software. So there are enough memory in the GPU to host that 19 layers of MOE. But when I'm recording, Virtual avatar software is using additional memory from the GPU, and this means that I no longer have enough memory to host 19 layers of MOE. So that's why this startup script will not work when I'm recording, because I simply don't have the memory to host 19 layers of MOE. That's why it is important to take note of your memory usage in your system, and when you are starting a LLM model, you need to take in account of available memory in your GPU, as well as what are the additional memory usage that you may use after starting the LLM model. So in this case, you may be running a game, or you may be running any other software that may use memory on your GPU. Then in that case, you will have to readjust this parameter to ensure that you have enough memory to run everything that you are planning to run, including your LLM model. So how do we find the perfect number of layers to offload to GPU and still be able to run whichever software that you want to run? So the first thing is we run whatever software that you wanted to run, get them all up and running, and then we will start with all the layers pushed to CPU. Okay, now that the model is started and we have configured all 40 layers of the MOE on the CPU, now we will test again on the speed generation, how fast is the model. As you can see right now, it is significantly faster, right? We are looking at 31 tokens per second, and the response seems acceptable as of now. So how do we further improve on this? So now we stop this model, and you can see that in my GPU, I still have around 10 GB of VRAM available. So now what we will do is, we will slowly cut down on the layers that we will push the MOE to our GPU, because we currently have space in our GPU, right? So we will offload some of the layers to our GPU for faster processing. So in this case, we will run it on 40 layers, right? So now let's set to I have 10 GB, so let's set it to 33 for now. So we slowly find the perfect number that we should offload to the GPU. So now the model is started again, and then we can actually refresh this, and then we will see again how well it is right now. Okay, so now you can see we are running at 35 tokens per second, right? I mean, not significantly faster, but slightly faster than before, right? So this is what we will do. We will slowly cut down on the numbers that we are pushing the GPU to maximize our GPU, so that we can speed up the model. Right, so we are getting a consistent 35 tokens per second, right? Yeah, this is great. So now we stop this, and you can see that I still have 7 GB of free memory in my GPU. So we just continue to find the perfect number of MOE to push to our GPU that we can actually host on our GPU. So let's move it to 25. Right, so we will have 25 layers on CPU and then 15 layers on GPU. And we'll see what the improvement we will get with this configuration. So now the AI is running. We can test again. Right, so now we are getting 40 tokens per second. So you can see, right? So the more layers we offload to GPU, the fastest we will get. So it's constantly around 41 tokens per second. Right, now this is usable, right? Changing a few numbers in the parameters, we can actually change the performance of our model running in our system. So now we will check again. So I have 890 MB left. So should I push another layer? We can try, right? So let's see, if I were to change it to 24 and I'll push 16 layers to GPU, we will see if that works. And note, this is on top of running my recording software and my virtual avatar software. So if I'm not running this, I could push more layers and I could get faster response in the model. So now it is running. We can test again. Now we are getting around 42. A slight improvement, not much, but better than nothing. I mean, we are looking at maybe around 1 token more. And then we also have to check on how much memory it has taken in our GPU and whether if there are still any free space that we can use. So now it's done. So we can see we have 628 MB. I think that is a decent amount to live for. So next, now that we understand how to divide the layers of experts between the CPU and GPU, and how do we effectively make use of our memory in our system to run the model properly, the next parameter we are looking at is actually no map. So for no map, which is this parameter, what we are looking at is, by default, Llama is trying to be smart with your memory. What it does is, it shows you that the model are loaded into your RAM, but in reality, your model is still on your drive. It is only loading the necessary pieces when needed from your drive and unloading them afterwards to make space for others. So while it sounds smart on memory management, but you need to understand that now we have an additional step of loading the necessary part of the model to RAM before processing our inputs. Therefore, we may see slower speed in our local LLM model response. By using no map, we are telling llamacpp to force all our model into the RAM. Whether we see any improvement depends on the model and the hardware you are running. Also to note, you should only run these parameters if you have enough memory to hold the whole model. So let's give it a try. So I take the previous startup script and I add no map, and then I'll start the server. Okay, so now that the server are started, we will test on whether if there are any improvement. Okay, we do see a bit of improvement here. So originally, I think our local RM was around 41 to 42 tokens, and here we can see we are actually running on 44 tokens. So we are seeing an improvement of like 2 tokens. So there are some slight improvement with no map parameters. So with no map, we do gain a bit of improvement. Now we have gone through improving and optimizing our local LLM model that will work on any hardware. We'll look at reclaiming our memory. What do I mean by reclaiming our memories? Didn't we just assign all those memory effectively to our LLM model? Yes, you are right. But no, there are still ways to squeeze out more memory, and that is to optimize your KB cache. Remember all the points about GPU and CPU memory from before? Context size also play a part in determining your allocation of layers between GPU and CPU. Why? Because the lesser free memory we have in GPU, the lesser context window we can fit in. So why does the size of the context window play an important part of the setup? Because smaller context window means lesser amount of input data can be processed, couldn't handle complex tasks, whereas bigger context windows means we can run more complex tasks and provide more input data. Every token the LLM model processes, it remembers as a key and value pair, also known as KV cache. Therefore, the bigger context windows, meaning more tokens being processed by the model, more space will be required for KV cache. Therefore, it is important that we keep some space on your GPU for your context. So you understand what is the problem we are facing now? We need to load as much as possible into GPU to speed up our local LLM. But at the same time, we also need to leave enough space for us to use it with a decent context windows. If we load more layers in the GPU, this results in faster LLM model response, but smaller context windows for us to use. If we don't load as much layer into GPU, just to free some space for a bigger context window, we will have a slower LLM model. This is a dilemma between speed and capabilities. So how do we choose? Well, it is actually not as difficult anymore. Google have recently in March introduced an compression algorithm that optimally addresses the challenge of memory overhead in vector quantization, or in other words, a compression method that achieves a high reduction in model size with zero accuracy loss. So the key here is it allows the reduction of KV cache size while still keeping zero accuracy loss. So with these new compression methods, you can massively increase context window like by around 4 times without hurting the performance. So here we are looking at this TurboCons. So it's a compression method that achieves high reduction in model size with zero accuracy loss, as I mentioned earlier. And this allows us to use more context without increasing the KV cache. And here we are looking at some data that someone has already performed with this new compression algorithm. So here we can see that if we are running on a 32,000 context, 32K context, the KV cache is around 4 GB under F16. And if you are running on a 100K context, it is actually around 12 GB. But with this new compression method, 100K context now only occupy 2.8 GB. So we can see that there is a reduction of memory required with this new compression method. So now we can actually run higher context while using lesser memory. So this is how we reclaim memories from our GPU so that we can actually offload more layers to GPU to further improve our LLM model. However, there's one thing to take note. The main llamacpp master branch, which is the standard fork, it doesn't support TurboCon yet. So you will have to actually build your llamacpp under this feature branch in order to use the TurboCon. So I'm not able to demonstrate this as I'm using the master branch of llamacpp. So if your llamacpp is actually running on this branch, you can actually try to configure your LLM model KV cache using Turbo tree compression methods. So there are two main benefits to using this Turbo tree compression method for your KV cache. One is you're able to use a larger context window while using lesser memory. Second, the memory that you save from the context window can be used to put more layers into your GPU, which will then further increase your LLM model speed and response. As mentioned, since I'm not running on that branch with my llamacpp, so I can't really run the compression method, but I'll show you what you need in the parameters in order to run that compression method. So here we can see CTK and CTV. So these are cache type K and cache type V. So these two are the one that we determine the cache compression method you are going to use. So in this case, you are actually going to run this cache type K turbo tree and then cache type V turbo tree. So by running these two, you are actually configuring the cache type to use Turbo 3 compression method. So with these two parameters, you are now running on the compression method that will save space and allow you to run bigger context window. So to summarize, we have gone through 3 points. First, proper memory allocation for your LLM model. This is very important and it is always the main culprit whether your LLM model runs properly or not. Second, no map. So we load all our model into the RAM to prevent additional step of loading and unloading of memory by llamacpp. Third, new cache compression method that allow us to run bigger context window while still keeping the size small, allowing us more memories in GPU to run more layers of our model. This allows us to run more complex tasks with fast speed even if our hardware are not high-end or built for AI. Putting everything I've gone through in this video together, we should see significant improvement to our LLM model speed from something that is slow to something that actually feels decent, acceptable, and usable, all on the same hardware. And if you can recall from my previous video, in the initial LLM setup, my LLM speed was around 7 tokens per second. Through the points that we have gone through today, we can see that my LLM now runs at around 44 tokens per second. That is a significant improvement to our LLM speed. So the proper configuration of your LLM is actually very important. And I would like to thank Chronosone77 for explaining some of the things that I do not understand in the comment in my previous video. I really appreciate the comment. If I have provided any wrong information, please feel free to leave a comment to correct me. Or if you have any knowledge that you wish to share, please also leave a comment so that everyone can learn. So that's all for this video. If you like my content, please kindly subscribe to my channel. I greatly appreciate your support. Thank you and I will see you in the next one. Bye bye.